The easiest atom to deal with is the hydrogen atom. The hydrogen atom has a nucleus which involves one proton, and that means the neutral hydrogen atom has one electron. And so we only have one electron to worry about in terms of where that electron is. But that electron can be described by a whole number of different quantum numbers. So I could describe that electron in terms of 1, 0, 0, which would be a 1s orbital, or I could describe it as a 2, 0, 0, which would be a 2s electron, or 2s orbital distribution, or it could be 2, 1, 0, which would be a 2p. It could also be 2, 1, minus 1, or 2, 1, 1. All of those would be 2p orbitals. I could describe it as a 3, 0, 0, which would be a 3s orbital distribution, or it could be 3, 1, 0, 3, 1, 1, or 3, 1, minus 1, all of which would be 3p, or since when I'm in n equals 3, I can go up to L equals 2, I could have 3, 2, minus 2, 3, 2, minus 1, 3, 2, 0, 3, 2, 1, or 3, 2, 2, and all of these would be 3d orbital distributions. And I could keep going. So all of these different possible distributions, which I shorthand in this notation where I give the L quantum number is represented by a letter, S, P, D, or F, and the N quantum number is out in front of that letter, which designates the L1. Notice again that in this shorthand notation, I'm not telling you anything about the orientation. All of these orientations look exactly the same, basically. They're just oriented differently. So I just call all of those 3p. So remember that we said that the N quantum number represents something about the energy that that electron would have. So if it was in this distribution, N is the smallest, so it would have the lowest energy. So in that distribution, I would have the lowest energy. And then as I go up, the energy increases. Now, for the hydrogen atom, the only quantum number that matters for the energy is the N quantum number. So that means that all of these, because they all have N equals 3, have the same energy. And all of these, because they all have N equals 2, have the same energy. And then the N equals 1 has the lowest energy. So if I was to draw a picture, a diagram, to represent those energies, then I would do energy increasing along the sort of y-axis, if you will. And I would put my 1s down here at the lowest possible value. And then my 2, N equals 2, orbitals would be here. So this would be both the 2s and the 3 different 2p orbitals would have this energy. And then I would have N equals 3, which is all the 3s, the 3p, and the 3d orbitals all have that same energy. And then I would have N equals 4, and then I would have N equals 5, etc. Okay, so you'll notice that I've made these energy levels closer and closer together as I go up. And that's because I happen to know that the energy of a hydrogen atom is represented by a particular relationship to the N quantum number. So by convention, we say that the energy is 0. So up here is energy equals 0, and all of these energies are negative because we set the 0 of energy when the electron is no longer interacting with the nucleus at all, and so it's completely not part of the atom. So when I'm up at equals 0, I don't really have an atom anymore because I've removed this electron and I just have this bare proton. So because we're free to set the 0 of energy wherever we want, that's where we put the 0 of energy. And so all of these are negative. And the energy associated with any n level for a hydrogen atom is minus a constant, which we're going to represent as R sub h, divided by n squared. So this R sub h is what's called the Rydberg constant. And it has the value of 2.17 times 10 to the minus 18th joules. So that Rydberg constant is a constant, and the energy then only depends on the n value of my particular orbital, which describes the electron. So if the electron is in any one of these n equals 3 distributions, it has an energy that is minus R sub h divided by 9, because 3 squared is 9. And if it's in any one of these n equals 2 distributions, it's going to have an energy that is the Rydberg constant, negative, divided by 4. And if it is in this distribution that's described with an n equals 1, then it's going to have minus the Rydberg constant divided by 1. And so because this n is squared, that has the effect of making these energies closer and closer and closer together as I get up towards this limit of E equals 0.